Hi, Mr. T here, helping out with Level 3 Chemistry. In this video, we're going to be looking at Achievement Standard 91388 spectroscopy. In particular, we're going to be looking at mass spectrographs and how we interpret them. If you find this video helpful, don't forget to share, like, and subscribe, and look out for new videos. Okay, so let's have a look at how mass spectroscopy works. So mass spectroscopy is a technique used to identify what a molecule is constructed of. And essentially what we do is we take a molecule and we place it into the end of a spectrometer. The first part of the spectrometer is an ionizing chamber. We put a large voltage electricity through there and we break the molecule up into little fragments. So if I was to take this molecule here, which we can see is an ester, it's methyl propanoate. It will generally fragment either side of the carbonyl group or the carbon double bond oxygen group, and maybe just the other side of the oxygen as well. So we'll break it here. You can see that we can get this CH3 fragment. Notice it has a positive charge. And then if we break it to the right of this oxygen here, or in between the oxygen and the carbonyl group, we can get this fragment here. Okay, which is the CH2, CH3, C double bond O. And also it can fracture on the other side of the carbonyl group, and we will get from there this ester fragment on the left, and we can get this C2H5 fragment on the right. Also, we get the whole molecule traveling through with a positive charge that hasn't broken up. So the ionizing chamber just really shakes it about and breaks it up into pieces, or doesn't break it up into pieces, and then the particles start to travel through the rest of the machine. Right, okay, the mass spectrometer, after it's the different size particles have left the ionization chamber, they're going into this area that has a magnetic field that's produced by an electromagnet. Now the electromagnet will has electric current going through it that produces a magnetic field. Now the size of the electric current varies over the time that the particles have been detected. Now if you put a small electrocurrent going through here, you can deflect small particles onto the amplifier and they can be plotted on a graph. So you can change the strength of the magnetic field, which will then change the size of the particles that will hit the amplifier. So a small magnetic field a small current, small magnetic field will deflect small particles on the amplifier, a medium one will deflect medium-sized particles, and a large current will deflect the largest particles onto the amplifier. So what you get here is all of this information that we get, that is the amount of particles that are deflected at different currents or detected at different currents are plotted on a graph, and we end up with this mass spectrum graph here. So this is a mass spectrum graph of methyl propanoate. What we can see here is that we have a lot of particles here at 27. We have a reasonable amount also at 58. And we have a reasonable amount here at, what is that, 88. So the relative abundance of these particles, and that is compared to the highest peak. So 100 is the peak that has the most, and then the relative abundance of particles is measured, and the mass per charge. Really what it means is that a peak that is at 27 means the particles here, 100 abundance, there is a whole lot of particles with a mass of 27, and there's a whole lot of particles with a mass of 57 here, 57 here, and a whole lot of particles with a mass of 88. Now this graph is really useful because when we know the size of the different particles that make up a molecule, we can put them back together like a puzzle to work out what the original molecule was. Okay, so we produce this mass spectroscopy plot or graph, what does it actually mean? Well, let's have a closer look at it. So we have these peaks. Remember, they're measured in mass per charge, but actually the mass per charge, a peak that has a mass per charge of 57 actually means that there is a fragment with a molar mass of 57 grams per mole. So the first thing to notice is that these peaks, remember, are caused by the fragments we talked about in previous slides. Now this one here at the left here, this fragment, this peak at 15 is produced by this fragment CH3. Now the reason it's 15 is the carbon has a molar mass of 12 and each hydrogen has a molar mass of 1. That gives us 15. If we go to the next peak here, we can see that it has it's at 29, so this is our largest peak by relative intensity. It's going to be the next fragment we have here, which is a CH2CH3 fragment that came off this methyl propanoate. Now remember, we also had this part here that came off, 57. That's the fragment from the right hand side. We have 59, this other fragment, and last but not least, we have the whole molecule with a positive charge. So this is the actual molar mass. So you see this, quite the higher peak on the right hand side is the maximum peak, has a molar mass of 88. That means that the molecule that actually went into this, originally into this mass spectrometer, the molar mass is 88 grams per mole. Another thing to notice is the little wee one down the bottom here. Now this is, we're going to talk about this in the next slide, but this is actually called our M+1 peak. M+1 peak, and this is actually comes about from something called a carbon-13 isotope. Okay, so let's have a look at another spectroscopy graph on a different molecule. This molecule here is methylbutane or 2-methylbutane. We can see here that we have this peak right down at 72. This is the M+ peak. Now the M+ peak is the peak caused by the molecule without being fractured or broken. It has a plus because the molecule is given a positive charge as it goes through the ionization chamber. Now because the peak is at 72 mass per charge, or M per Z, its molar mass is 72 grams per mole. Notice also down to the bottom right of this peak we have just a small accompanying peak. This peak is called the M+1 peak. Now the M+1 peak comes about because each carbon that has a molar mass of 12, there is actually 1% of the carbon atoms that have a molar mass of 13. Now in this molecule, because there are 5 carbons that have a molar mass of 13, then you're going to get about 5% of the you're going to get a molar mass of +1 with about 5% of your fragments when you take in having these 5 extra carbons at 1%. So it's about 5% of the height, or 3 to 5% of the height. And the reason that I'm mentioning this is we disregard this. This isn't the peak at our furthest right. The peak at the furthest right is the blue one, which we call the M+ peak. And we just acknowledge that there is the M+1 peak, but we ignore it. Okay, so we need to calculate the mass of the fragments. Or usually what we do is, if we see a molecule, we can think about the fragments that it's made of, and we can relate them to the different peaks. So this molecule has a mass of 72, so we are comfortable that this fragment here, the M+ fragment, is going to be down here at 72. We can then see that we can cut this right here, right? So on the left hand side we have this fragment here, which is a butyl fragment. It has a molar mass of 4 carbons, 4 times 12, plus 9 hydrogens, which gives us a total molar mass of 57. So we expect that there's going to be a relative abundancy peak at 57 M per Z, and we have it right here. So cool. So notice if we keep going this, we can see, okay, we'll cut here. We'll also have a fragment that's a propanol or propyl fragment. It is going to have a mass of 43 because we have 3 carbons, 7 hydrogens, they add up to 43. So this 43 peak comes about from this fragment, and we can see that the last one that we might see here or recognize is this fragment here, which is 2 carbons is 24 plus 5 hydrogens. So we should have another abundancy peak at 29, which we do, which is this peak coming about from this fragment here. Okay, so when we look at a mass spectrometer graph, there are common fragments that we're going to see. So there are common fragments that are produced from organic molecules, so there are common peaks that we should see at certain numbers. So with alkyl fragments, that is just carbon and hydrogen fragments, we should see 15s, 29s, 43s, 57s, 71. Okay, these are our fragments. The amine and amide fragments, we see, notice they're even, 30, 44, 58. The amides 58, 72, carboxylic acids 43, 70, 57, 71. Notice that carboxylic acids fragments are actually similar. They're the same peaks as alkyl peaks. So we have to use other evidence actually when we have either carboxylic acids or alkyls. We can't distinguish between them. But esters, they're the ones here in the light pink, they commonly have peaks at 59 and 73, which is different than the 58 and the 72 we see from the other one, or the 57s and 71s. Alkenes, we're going to see peaks at 41 and 55, a bit smaller where the peaks are compared to the alkyls because they are 2 hydrogens shorter. And bromines, chlorines, we're going to see peaks 49, 51 for a fragment. Notice that we'll see actually 2 peaks, and they're going to be in a 3-to-1 ratio. Now we're going to go over that in the next slide. And when we have bromines, we're going to have peaks at 2 apart as well, 93, 95 if you have 1 bromine and 1 carbon, or 107 and 109 if you have 2 bromines and 2 carbons. Okay, so in this slide, let's see why chlorines produce a double peak. So the reason for that is chlorine actually has 2 different isotopes, or 2 different versions of the chlorine atom. Now that comes about because one version of the chlorine atom has 18 neutrons, and one version has 20 neutrons. They both have 17 protons. So you actually get 2 versions. You get a chlorine 35 and a chlorine 37. Remember, different numbers of neutrons in their nucleus. Now chlorine 35, if I was to just take a big pile of chlorine atoms, then 75% of them would be the lighter 35s, and 25% of them would be the heavier 37s. What that essentially means is every time I make a molecule that has a chlorine, then 25% of them will be, 25% of them will be 2 molar mass units heavier than the other 75%. Now this actual ratio in peaks is a 3-to-1 ratio, and we can see that here. Here's our height of 3 from our 35 to 1 from our 37. Notice also these peaks are 2 molar mass units apart, or 2 mass units apart. We also notice, if we see that at the end that there is this 3-to-1 ratio, there's going to be a fragment that also has a 3-to-1 ratio, and here it is here. So we're going to see this 3-to-1 ratio at another part of the graph. So this is a really good indication that there is a chlorine atom in a molecule. There is a 3-to-1 ratio, and we have what's called an M+ and an M+2 peak. So the M+ is what we would expect if we added it up with 35. The M+2 is the molar mass plus 2 peak that we're going to see, that is a third of the height, that's going to be 2 mass units further on. Okay, so bromine, bromine's a bit like chlorine in that it has 2 different isotopes that it appears in naturally, commonly, and so these isotopes are actually bromine 79 and bromine 81. They are roughly in a 50% to 50% ratio, or 50 to 49%. So we're going to have 2 peaks. Now, because these 2 molar mass, these 2 isotopes have 2 difference between their molar mass, the peaks are going to be 2 units apart on our graph. And the one on the left is called the M+ peak, and the one on the right is the M+2 peak. So if we see these 2 peaks, we know there's going to be a bromine in the atom. Here they are here, the M+ and the M+2 peak. So we're also going to see this 1-to-1 ratio in other fragments. So notice that here in other fragments. So this is a really good indicator of a bromine. We're going to see these twin peaks at different points throughout this plot, and that means that there is a bromine, a fragment with a bromine atom attached. So often we put esters, and the molecules we have are esters, and an ester has an interesting fragment in that when it breaks apart, it's going to produce a specific unique peak. Now, our molecule here is an ester. This is methyl propanoate. If I was to look on the right here, we can see the peak for the M+ peak, the molecular peak. It's at 88. If we're going to break this molecule apart, we can see that we can break it either side of the carbonyl group, so on the left here. And this fragment here is actually a common fragment, because it's also a fragment we would find from a carboxylic acid, and it has a mass of 57. That is also the mass that we get from a butyl group. So that this fragment here isn't a unique size, so it's going to be hard to be used to determine this is an ester. However, if we break on the other side of the carbonyl group, what we actually have is now we have a group that has 2 oxygens attached to a carbon, and that gives us a different size fragment that we would normally wouldn't get from most most fragments. So we get this size here, which is 59. This 59 is a distinctive peak for an ester. So if we see a 59 peak, we're going to be thinking, okay, possibly this molecule might be an ester, because we can see a peak at 59. There's going to be a fragment with a molar mass of 59. So as well as 59, another common peak that esters could have, if it's a larger ester, is 73. And if you're seeing a 59 or 73, you're thinking, hey, this possibly could be an ester. Okay, amines. What makes amines special? Well, amines are special because they have a nitrogen joined to the carbon chain. Now, nitrogen is different than the other atoms that we use in these molecules because it actually has an odd number of atoms attached to it, and it isn't a terminal attachment. So what I mean here is we're going to get this M+ peak here as an odd number. So usually we get an even number for an M+, but if we get an odd number for an M+, it means that we have a nitrogen in our molecule. See the nitrogen here, how it's attached to 1, 2, 3. It only has 3 bonds instead of a carbon usually has 4. What that means is we are now going to have an odd number of hydrogens. So we've got 1, 2, 3, 4, 5, 6, 7. Now if I'd had an oxygen there, I would have only had 1 other hydrogen attached. I still would have had an even number of hydrogens. But a nitrogen means there's going to be an odd number of hydrogens, and hence there's going to be an odd molar mass. So if you see an odd molar mass at the end, you're either going to have an amine, or possibly you might have an amide, which also has a nitrogen. Notice, look, we've also got this fragment here. which is just has 1 carbon and 1 NH2. It has a molar mass of 30. This 30 fragment is also what we would expect from a nitrogen carbon with 4 hydrogens attached, so that is another indicator that could be an amine. But the big giveaway is we have this odd number of our M+ fragment. Okay, so let's summarize this. So if we start from the smallest fragments we can get, we have this fragment of an methyl group which has 15 molar mass. We have an ethyl group that has a 29. We also have now this amine, this methylamine group that has a 30. We have this group with 3 carbons, but we have a double bond. It's got 41. Notice here that both the propyl group and the carboxylic acid group that has 2 carbons has the same molar mass of 43. We have the an amine with 2 carbons has a molar mass of 44, and then we have another double bond with 4 carbons as molar mass of 55. Then we have again the next the butyl group, and we have 3 carbons for the fragment that comes from the carboxylic acid or possibly an ester is also going to have 57. So notice that these fragments of 43, 57 aren't very definitive. They don't help us determine very well what our molecule is, but it will kind of indicate how big our molecule is and where some major structures are. Here's some more amines and amides, and then we get into this. Remember that light pinky color here is our ester group, that specific number of 59, and the specific number when we go further on here of 73. That's what we'd expect if we saw an ester. Remember, if we see these fragments as even numbers, big, tall, even numbers, we're going to be expecting that we have a nitrogen in here. And this is kind of what you might be expecting or having around you to help sort of identify some of the fragments you might see from your peaks. Remember again, the chlorines have these double peaks. They're the 3-to-1 ratio. And then we have our bromines that have these double peaks with a 1-to-1 ratio. So just one more time, these are the common fragments that you need to know. Make sure that you become familiar with these. You don't really have to remember them as such, because when you start to determine what your molecule is and you're sketching it out, basically what you'll be doing is sketching it out and then determining what fragments it could possibly be, adding up the molar mass for that fragment, and then just seeing does that agree with the peaks that you see on your graph. And that is really what we do with a mass spec graph. Is we take the peak on the right hand side, which is going to be our M+ peak, and we find the molar mass of the molecule, and then we see if we can determine the different fragments to work out exactly how the molecule is constructed. But we don't use this in isolation. We're going to use these mass spec information along with carbon 13 NMR graphs, and we're going to use infrared spectrographs as well. And when we use all 3 of these graphs together, we can determine what our unknown organic molecules are. Okay, hope this has been helpful. Look out for the next video. Okay, if you've got to this part of the video, you've obviously watched all the examples that I had on those 3 questions. Hopefully this has fortified your understanding of geometric isomers, and you are now well prepared to go and attack that exam. Good luck, and if you found this video useful, don't forget to like it, subscribe, and look out for new videos that I might put up by clicking that bell. See you later.